Alright, before we actually get to the calculus of residues, which is a rather large and computational subject, we're going to take a look at a few of the theoretical consequences of the residue theorem, if you will, or of the things that we know so far about Laurent expansions. And it'll revolve around the idea of what happens at a zero, what happens at a pole, and then also what happens to real valued functions on the real line. How do those things expand into the complex plane? And that's the reflection principle. Okay, so what do we have? If a function is analytic and has a 0 at z0, then 1 over f has a pole there and vice versa. So that means it makes sense to analyze zeros and poles at the same time. And an important goal there is that we'll be interested in results that allow us to efficiently compute residues, or if we don't memorize the results, and I really haven't done that, but even if we don't do that, then at least we have practice with the methods to compute the residues, because in the end this is glorified algebra of power series, and that's something that, although it can be tedious, it shouldn't be difficult in principle. We'll also derive some results that show that analytic functions are uniquely determined by a surprisingly small number of values. It's still an infinite number of values, so for those who aren't going deeper into mathematics to the point where infinity comes in different sizes, surprisingly small here means that it's just a very thin subset of the domain that actually determines all the values of an analytic function, which is actually quite amazing, because on the real line, if a function is taking certain values on an interval, it can still have very pretty properties and take entirely different values on an interval that is a couple of units away from that. So let's see, in terms of zeros, if the function f is analytic in the neighborhood of z0 and f of z0 equals 0, then the smallest m, so that the m's derivative at z0 is not equal to 0, that's called the order of the zero. And the theorem that goes with that is that if f is analytic in the neighborhood of z0, then f has a 0 of order m at z0 if and only if there is a function g that is analytic in the neighborhood of z0. G of z0 is not equal to 0, and f of z is equal to g of z times z minus z0 to the m for all z in that neighborhood. So that is quite reminiscent actually of that theorem that we had just proved about poles, where we factored out a 1 over z minus z0 to the m. And the proof is actually also quite similar. F is analytic, and that means that f is the sum n equals 0 to infinity. So suppose f is analytic, period. Therefore, f has this power series expansion, sum n equals 0 to infinity a n z minus z0 to the n for z close to z0. And if f now has a 0 of order m at z0, then we have that 0 is equal to a0 all the way through am minus 1, because remember, these guys are computed with the 0th derivative, first derivative, all the way to the m minus first derivative, which are all equal to 0. And that means that f of z is the sum n equals m to infinity a n z minus z0 to the n. And we can factor out a z minus z0 to the m here. And then, let's see, that would give us an exponent n minus m, and k equals n minus m gives us n equals k plus m. And if k is n minus m, then n equals m means k equals 0, and n going to infinity means k going to infinity. So just factoring out and re-indexing done at the same time here. Conversely, if f of z is equal to, and that thing then is g. So conversely, if f of z is z minus z0 to the m g of z, for z minus z0 smaller r and g being analytic with g of z0 not equal 0, well then f of z is equal to this z minus z0 to the m times the power series expansion of g, which I give coefficients cn, where c0 is not equal to 0. And that's the sum k equals m to infinity ck minus mz minus c0 to the k, because if I pull the z minus c0 to the m in here, I get n plus m, I set k equal to n plus m, and the same, or a similar transformation as what we did up here, changes the sum to this form. And that, of course, means that f has a 0 of order m here, because the low order coefficients all the way to order m minus 1 are all equal to 0. As an example, well, the sine function has a 0 of order 1 at z equals 0, and that's because the sine function's power series expansion goes with these exponents 2j plus 1. Of course, we have to get the coefficient right, but what we're really focusing on is that it only has odd exponents. That means we can pull out a z, everything else stays the same. The 2j plus 1 turns into just a 2j. And well, that's it. That is, by the previous theorem, what it means to have a 0 of order 1. The function 1 minus cosine z has a 0 of order 2 at z equals 0. Same story. 1 minus cosine z is 1 minus the power series expansion of the cosine, sum j equals 0 to infinity, negative 1 to the j over 2j factorial z to the 2j. And for j equals 0, we get a 1, which means we can cancel the 0th term and end up with negative sum j equals 1 to infinity, negative 1 to the j over 2j factorial z to the 2j. And then I set k plus 1 equal to j, which gives me k plus 1 here, k plus 1 here, k plus 1 here, which of course then becomes 2k plus 2. And if j is equal to k plus 1, well, when j is equal to 1, then k plus 1 equals 1 gives us k equals 0, so we get a regular analytic function here. But now I can pull out this extra z squared, and I do so. So this is z squared times negative sum k equals 0 to infinity, negative 1 to the k plus 1 over 2 quantity k plus 1 quantity factorial times z to the 2k, and that's what it means to have a 0 of order 2. Okay, now let's let f be an analytic in a neighborhood of z0. Let it be 0 at z0, and let it not be constant, which means in particular that the function is not completely equal to 0 in any neighborhood of z0. So it's got a 0, but it's not constant in any neighborhood. Then there is a deleted neighborhood, 0 smaller z minus z0, absolute value smaller than delta of z0, on which f is not equal to 0 at all. So we have to be very careful here with the language, basically because the function is not constant, f is not identically equal to 0 in any neighborhood, but it could still be that f has zeros in the neighborhood. And what this theorem says is that if there is a 0 of an analytic function, then there is a deleted neighborhood within which there aren't any other zeros. The proof is, well, because f is not identically equal to 0, the power series expansion about z0 is not equal to 0. And that means that f is a n z minus z0 to the n for z minus z0 smaller r for some r greater than 0. And because f of z0 is equal to 0, we have a equals 0. So with m being the order of the 0 z0, which is not infinity because the function is not identically equal to 0, we have that f of z is the sum n equals m to infinity a n z minus z0 to the n, which is z minus z0 to the m, sum k equals 0 to infinity a k plus m z minus z0 to the k, similar to what we've just done a couple of panels ago. And well, now because power series are continuous, there is a delta greater than 0, so that this power series is not equal to 0 for z minus z0 smaller delta, because am was not equal to 0. Yeah, because am was not equal to 0, because m is the order of the 0 z0. So that means the power series is not equal to 0 in a neighborhood, and z minus z0 to the m is not equal to 0 for 0 smaller z minus z0 smaller delta. The only thing that means is that we must choose the delta smaller than z0 absolute value, or we can make it arbitrary if z0 is equal to 0. But that all certainly works out. And that means that f of z is not equal to 0 in a punctured neighborhood of z0, and that's what we wanted to prove. So that is geometrically kind of interesting. What that means is zeros of analytic functions cannot cluster up. And that has a couple of neat consequences regarding the uniqueness of analytic functions. Namely, if a function is analytic in a domain D, and if that function is equal to 0 on some subdomain or some line segment that contains z sub 0, so the domain need not be all of D, it just may be a subset of D, then f must be equal to 0 in the whole domain D. Well, the proof is, first, by the preceding theorem, f must be 0 on some neighborhood z minus z0 smaller r0 of z0, and that is because if the function is equal to 0 on some domain or line segment that contains z0, well, then it is equal to 0 at z0, and it has zeros that are not equal to z0 in any neighborhood of z0, and, well, that can only happen if the function is constant on some of those small neighborhoods, and so there are some neighborhoods on which f must be equal to 0. Completely, it must be identically equal to 0. Now let z1 be any point in the domain of D. In the domain D. Well, then there is a path C from z0 to z1. Let's visualize that. Here's z0. Here's a neighborhood on which the function is equal to 0. Here's z1. And here's a path that goes from z0 to z1. What we can do then is we can let gamma be a parametrization of that path. And that means that f of gamma of t is equal to 0 on some interval 0 to delta, because after all, around z0, the function is equal to 0. By continuity of the composition of f with delta, we must have that f of gamma of t is equal to 0 on some interval 0 delta with delta being closed. That is, that's continuity. We have an open interval here, and we can then extend that to a closed interval. If a function is 0 all the way up to delta, then it must also be equal to 0 at delta. And now I want to choose delta to be as large as possible. So that delta is somewhere here. And now, however, I can do the same argument, because on this line segment, on this curve, the function has been equal to 0 all the way up to gamma of delta. That means I can find a neighborhood of gamma of delta on which the function will be equal to 0, and that means I can actually expand to delta plus delta tilde, and that's a contradiction. So let's see how this keeps going. I've chosen delta to be as large as possible, and I suppose for a contradiction that delta is smaller than 1. That's when we're in this previous picture that our gamma of delta is not at z1. Well, then we let z tilde be gamma of delta, and then the same argument as we applied at z0, f must be equal to 0 on a neighborhood z minus z0 smaller r tilde of z tilde, and that means there must be a delta tilde, so that f of gamma of tilde, gamma of t, is equal to 0 on the interval from 0 to delta plus delta tilde, and that contradicts the choice of delta. So that means that delta must be equal to 1. That means f of z1 is equal to 0, and z1 was arbitrary, so f must be equal to 0 in the whole domain. Okay, so that means that analytic functions may be defined on a weirdly shaped domain as long as it's connected if in some corner of that domain we have that the function is equal to 0 on a line segment or something like that, then the function must be equal to 0 everywhere. In particular, if a function is analytic in a domain D, then it is uniquely determined by its values in a domain or a line segment that is contained in D. So, for example, proof, if f and g are analytic and they're equal in a domain or a line segment contained in D, well, then their difference is 0 in a domain or line segment contained in D. And that means, by the preceding result, that f minus g is equal to 0, and that means that f is equal to g. Yeah, okay, so f minus g is equal to 0, in a subset by the preceding result, f minus g is equal to 0, and that means f is equal to g, and that's it. Okay, so that means if f is analytic in some domain and it can be extended to an analytic function on a larger domain, then this extension is unique. And that's very important because quite a few functions that we're interested in on the real line actually can be extended to analytic functions on a larger domain, on something inside the plane, and yet all those values in the plane are uniquely determined by the restriction of the function to the real line. So for example, here also another thing, the power series sum k equals 0 to infinity z to the k, that thing is defined on the disk of radius 1 around the origin, and the function f of z equals 1 over 1 minus z is not just one way to extend this power series to the whole complex plane, it is in fact the only way to extend this power series to the complex plane, except at the point z equals 1 where things go wrong. Okay, so the Schwarz reflection principle then can be seen in light of this remark that I made earlier, that we're often interested in functions on the real line which take real values. And if f is analytic in the domain D that contains a segment S of the x-axis, and which is symmetric with respect to the x-axis, so symmetric with respect to the real line, then f of z bar is equal to f of z bar on the inside for all z in the domain, if and only if f is real valued for each point on this line segment S of the x-axis that is contained in the domain. So our domain has to be symmetric, and we're only concentrating on this line segment here. So basically this is the situation that we may have a function that lives on a real interval or something like that, but it can be extended to the complex plane, and not only do we know that the extension is uniquely determined by what's happening on the real line, the extension also has a symmetry property, which is that we can pull complex conjugation in and out of complex conjugations in and out of the function. Okay, so that would be S here. All right, the proof. Well, first of all, if f of z quantity bar is equal to f of z bar for all z, then for all z in S, because those are all real numbers, we have that f of z quantity bar is f of z bar, which is f of z, and that means that f is real valued in S. Conversely, if f is real valued in S, we consider the restriction g of f to the upper half plane. Okay, so we're just looking at the upper half plane. We'll see the picture in just a minute. We'll then define g of z bar to be g of z bar for all z in the lower half plane that are symmetric to elements in the original domain of g. That defines a continuous function on D. Here's what's going on. We have S, and we have the upper half of the domain D, and that's where we set g equal to f. G is just the restriction of f to the upper half plane. In the lower half plane, we set g of z to be g of z bar bar, if you will. That's the same equation as what we have here, and that is continuous because, well, on the real line where those two are joined, the imaginary parts are 0, and that means, well, the real parts are going to be the same if we approach from above or from below, and the imaginary parts will be 0, so they'll also be the same as things meet, and that's what makes this a continuous function. Well, continuity is nice. We need analyticity. Well, analyticity comes from Morera's theorem. So now, moreover, if we look at integrals of g over closed curves, we claim that those are 0. And that's because the integral over every closed curve can be split into an integral in the upper half plane and an integral in the lower half plane. We'll take a look at the picture in just a second. Right here. So if we have any kind of closed contour, well, we just cut that through wherever z is, and if that contour bounces, well, then we'll cut it up into a bunch of pieces, but now the integral over c is equal to the integral over this upper half connected through S and this lower half connected through S, where, because in the upper half we go left to right and the lower half we go right to left, the integrals on the real line cancel. And because g of z is g of z bar bar, the integral in the upper half plane is 0 by analyticity of f, and the integral in the lower half plane is 0 because it's just the complex conjugate of the integral of f over the reflected curve. And so that means by Morera's theorem, because those integrals are 0, g is analytic. And because g is equal to f in the upper half of the domain, it must be equal to f on the whole domain, and that means that f of z bar is equal to f of z bar inside, because that's the equation that g satisfies, and we've just seen that g is equal to f. So that works for all z in the domain, and that is the Schwarz reflection principle. It has a couple of consequences. One of them is that because most of the time we're interested in functions that live on the real line and assume real values, for a lot of what we're going to do in the calculus of residues, we can just restrict our attention to the upper half plane, because anything that happens in the lower half plane is just the complex conjugate of what we have in the upper half plane. Okay, now let's take a look at poles. If we've got analytic functions p and q that are analytic in a neighborhood of z0, p of z0 is not equal to 0 and q has a 0 of order m at z0, well then the quotient p over q has a pole of order m at z0. Proof is quite simple. The expansions p of z sum n equals 0, a n z minus z0 to the n, and q of z being z minus z0 to the m sum k equals m, bk z minus z0 to the k minus m. We have that a0 is not equal to 0, and bm is not equal to 0, and that means that the quotient of the power series parts is analytic in a neighborhood of z0, and hence p of z over q of z is 1 over z minus z0 to the m. Hang on here. There we are. P of z over q of z is therefore 1 over z minus z0 to the m times an analytic function, and that means it has a pole of order m at z0. Okay, as an example, let's take the function f of z equals 1 over 1 minus cosine z. That has a pole of order 2 at the origin, and that's because 1 minus cosine z has an 0 of order 2 at 0, which we had already proved earlier. As a corollary, if p and q are analytic in a neighborhood of z0, p of z0 is not equal to 0, q of z0 is equal to 0, q prime of z0 is not equal to 0, then p of q has a simple pole at z0, and the residue of p of z over q of z at z equals z0 is p of z0 over q prime of z0. And the proof is, well, the fact that the pole is simple follows from the preceding theorem, and for the residue we recall that p of z over q of z is z minus z0 to the negative 1 times this analytic function, and then we just need to find the value of this analytic function at z0, and that value is a0 over b1, and that's p of z0 over q prime of z0, and that's it. Now wait just a second, did I overlook a negative sign here, or was that actually a typo on the previous panel? That actually was a typo. A minus m would have made that one work. So that was still okay. And so here we are with that theorem. This one actually is used quite a bit because quite a few poles in the calculus of residues are simple poles. Okay, the cotangent function, as an example, has a simple pole at the origin, and that's because cosine z over sine z is the representation, and cosine z is not equal to 0 at the origin. Sine of z has a 0 of order 1 there, as we had shown, and then we applied the preceding theorem. And the residue of the cotangent is then, of course, cosine 0 divided by the derivative of sine, which is cosine at 0, and that ends up being 1. If we want to find a more complicated residue, say the residue of f of z equals z over z to the 4th plus 4 at z0 equals 1 plus I, well, first of all, we should make sure that there actually is a singularity, but 1 plus I is square root of 2e to the I pi over 4, so that means there really is a singularity at 1 plus I, because if we take this thing, raise it to the 4th power, we get 4 times e to the I pi, which is negative 4, and that gives us a 0 in the denominator. And because z to the fourth plus 4 has 4 distinct zeros, the primitive or the roots of unity times root 2 here, we can apply the theorem because the 0 at 1 plus I will be a simple 0, and therefore the pole will be a simple pole. That means that the residue at z equals 1 plus I, z over z squared, z to the fourth plus 4 is, you just take the numerator, derivative of the denominator, and plug in z equals root 2 e to the I pi over 4. Well, that's root 2 e to the I pi over 4 divided by 4 times root 2 e to the I pi over 4 to the third. And, well, then I just did the computation directly. Let's see what happened here. E to the I pi over 4 and one of the e to the I pi over 4's cancels with one of the e to the I pi over 4's in the denominator, and e to the I pi over 4 squared is e to the I pi over 2, so that's where that comes from. 1 over the root 2's cancels with 1 over the root 2's, and root 2 squared is 2. 2 times 4 is 8, and everything in the numerator has been canceled, which means our numerator remains to be 1. And then that is negative I over 8. That is because e to the I pi over 2 is I, and 1 over I is negative I. Yeah. Now let's take a look at the behavior near singularities. This is a more geometric consideration. That's what we're closing with in this presentation. If f is analytic in a deleted neighborhood of z0, and z0 is a pole, then the function goes to infinity at that pole. And that's because if m is the order of the pole at z0, well, then for z minus z0 smaller than r, for some small radius, we have that f is z minus z0 to the negative m times an analytic function. Well, the power series converges to its value at 0, which is not 0 since the pole has order m. And z minus z0 to the negative m goes to infinity as z minus z goes to z0. And that's it, because now we have something that converges to a non-zero number times something that an absolute value goes to infinity. That product must go to infinity also. If f is analytic in a deleted neighborhood of z0, then z0 is a removable singularity of f if and only if f is bounded in a deleted neighborhood of z0. And that's if z0, and that's an if and only if, and well, if z0 is a removable singularity, then we have that f is a power series in a deleted neighborhood of z0, and that means that f converges to a0 as z goes to z0, and that means that f is bounded in this deleted neighborhood. Conversely, if f is bounded on a deleted neighborhood of z0, well, then we consider the Laurent expansion, because no matter what happens, as long as this thing is defined on a deleted neighborhood, it will have a Laurent expansion. Okay, now basically what we want to show is we want to show that the principal part of the Laurent expansion, sorry, the highlighting just doesn't work too well inside formulas, we want to show that the principal part is equal to 0. So we let m be a bound. Remember, f is bounded on a deleted neighborhood, so f of z absolute value is smaller or equal than m on this deleted neighborhood. Then for the Bn, we obtain, with C being a circle of radius rho between 0 and r around z0, we obtain that Bn absolute value from the formulas for the Laurent expansion is the absolute value of the integral over c f of z over z minus z0 to the negative n plus 1. I think I need a 1 over 2 pi I there. Well, indeed I do need that 1 over 2 pi I there. I just looked up that formula again. All right. Well, no matter. That's equal to the absolute value of 1 over 2 pi I integral over c f of z minus z0 to the n minus 1. And now realize that for small radii, this is going to be small. So now we pull the absolute values inside. Of course, we get a 1 over 2 pi I because the I goes away. Integral over c f of z absolute value z minus z0 to the n minus 1 dz absolute value, where we're integrating with respect to the arc length here. And that's smaller or equal than rho times m times rho to the n minus 1, the 2 pi. So basically it's 1 over 2 pi times 2 pi rho times the bound for f times the bound for the z minus z0 to the n minus 1. Well, that's m times rho to the n, and if we let rho go to 0, then that goes to 0. But remember that bn didn't depend on rho, which means if this goes to 0 as rho goes to 0, then the bn's must be equal to 0. And that means f has a removable singularity because the principal part of the Laurent expansion is equal to 0. Okay, I think this is the last one. You take an analytic function in the deleted neighborhood of 0, and we want to also talk about these essential singularities. And if f is an essential singularity, then for every complex number w0, for every epsilon greater than 0, and for all delta greater than 0, there is a z that is closer than delta to z0, so that f of z is closer than epsilon to w0. Basically what that means geometrically is that in any neighborhood of an essential singularity, the function is close to any value in the complex plane. So the function just oscillates crazier than we can imagine in pictures. If you think back to calculus, if you think about a function like sine of 1 over z, as z goes to the origin, that was a function that was near any number between -1 and 1. Well, if you extend this function to a complex function in the complex plane, then that function actually is near any complex number in any neighborhood of the origin. So that's this kind of infinite oscillation that gets really, really pronounced in the complex plane. The proof, well, suppose for a contradiction that this is not true, and what would that mean? That would mean that there is a w0 and an epsilon and a delta, so that for every z that is closer to z0 than delta, we have that f of z minus w0 absolute value is greater than epsilon, so that f of z is away from w0. Well, then I can take a look at g of z being 1 over f of z minus w0, and that thing will be analytic in a neighborhood of z0 because, well, the denominator isn't 0 in that neighborhood. Okay, and it's bounded there because f of z minus w0 absolute value is greater than epsilon. That means this thing is smaller than 1 over epsilon in absolute value. That means that g has a removable singularity at z0 by the preceding theorem. And that means the value that makes g analytic at z0 satisfies g of z0 being not equal to 0 because otherwise because otherwise this would go off to infinity, which it doesn't. It doesn't go off to infinity because it's bounded, and that means that this value must be not equal to 0. Give me a minute to think here. It's getting late in this presentation. Okay, sorry, that took me a minute. F of z minus w0 doesn't go to infinity as z goes to z0 because that would mean that f of z goes to infinity, and that would mean that we actually have a pole there, which we don't. And okay, so then we can take f of z minus w0 being 1 over g of z, that is analytic in the deleted neighborhood of z0, and it is bounded there. And that means that f of z minus w0 has a removable singularity at z0, and that means that f has a removable singularity at z0, which is a contradiction to assuming that this thing has an essential singularity, and that's it. Okay. Well, as you have seen or heard, some of this stuff does get rather involved, can and does get rather involved. We can't help that. That's how reality is in this situation, but what we have concluded here is a full case distinction of the behavior of analytic functions near singularities, and we can now move on and talk about the calculus of residues. I'm going to take a break. I'm not going to record another presentation today because it seems like I'm fading again, and at that time it's better to rest for a while than try to force it. I'll see you in the next one anyway. Thanks.